Well, welcome back. So we are again using the same book, Lecture Note on Analytic Geometry and Calculus by Dr. Stephen Moore, University of Cape Coast. So we looked at extrema of functions, and now we are looking at concavity and the second derivative test. So let's look at it. So we have concavity and the second derivative test. Concavity and the second derivative test. So let's look at these two diagrams in the book. Pk f of k. Another diagram here. Pk f of k. So here we have a downward concavity and an upward concavity. Okay. So let's look at the conditions by which a graph will have this concavity or that concavity. Okay. So if you have the function, you just have to use what we are coming to look at to test if the graph will exhibit this graph or the function will exhibit that graph. Okay. So let's look at how to test for concavity. So you have test for concavity. So let's write this. We suppose a function f is differentiable on an open interval containing C. And a second derivative, which is f prime prime of x, exists. Then let's look at these conditions. So then 1, f prime prime of c, f prime prime of c greater than 0 on AB. Sorry, so if f prime prime of c is greater than 0 on AB, then the graph is concave upward. It's concave upward. And 2, if f prime prime of c is less than 0 on AB, then the graph is concave downward. Concave downward. Concave downward on AB. Alright. So what it means is that you find the second derivative of the function, and knowing your critical values, you evaluate the second derivative at the critical values. And if the value is greater than 0, it it means the graph will have a concave downward. Sorry, will have a concave upward on that interval, okay, or at that critical value. And if f prime prime of c is less than 0, it means that the graph will have a downward concavity. Alright, so let me illustrate this. So for the first one, f prime prime of c is greater than 0. So let's say this is your c, alright? And if the derivative f prime prime of c is greater than 0 on AB, it means the concavity of the graph will be upward concavity. Okay, it means you have something like this. Okay, it moved from here to there, it means the concavity is going up. Okay, and this one is what? This is a minimum turning point, and we said that if, okay, we look at it in the second derivative test, so let's hold on with that and concentrate on this one. So if prime prime of c is greater than 0, this is what we are going to have. Okay, we are going to have an upward concavity. And if the second one, if f prime prime of c is less than 0 on AB, then the graph is concave downward. Okay, downward means we have to do something like this. Alright. So this just by the way, let's look at another definition for point of inflection. So point of inflection is also vital in testing for concavity. Okay, it's very, very important. So let's look at how to find the point of inflection. Let's look at definition of point of inflection. So a point PK, FK on a graph of a function F is a point of inflection. It's a point of inflection if there exists inflection if there exists an open interval AB containing K so that one of the following holds. One of the following statement holds. So let's look at those statements. A point K of f of k on a graph of a function f is a point of inflection if there exists an open interval on AB containing K such that one of the following statement holds. So let's look at those statements. So with those statements, we'll be able to find our point of inflection, or we'll be able to tell if a point is a point of inflection on a given graph. So we look at number 1 of those statements. Say f prime prime of x is greater than 0 if a is less than x less than k, and f prime prime of x is less than 0 if k is less than x less than b, or number 2, f prime prime of x is less than 0 if A is less than x less than k, and f prime prime of x is greater than 0 if k is less than x less than b. So if this one holds, then we say that the point k on the graph is the point of inflection. Okay, so this one, I think I will have to illustrate it over here. Please take some 30 seconds to finish writing it. I will clean so that we look at a diagram which is explaining what we have written here. Alright, so let's look at the diagram. So we have this, we have that, we have this, and we have that. So we have concave upward, we have a point here, let's call it P O I. We have another point here, P O I. We have another turning point here. So let's look at the meaning of this one. So here, for the fact say f prime prime of s greater than 0 if x is between a and k. Okay, so if f prime prime of s greater than 0, we say that we have a minimum turning point. So f prime prime of s greater than 0 gives us this one. Okay, this minimum turning point. Alright, so this is our k. Alright, so from here to there we have a minimum turning point, and f prime prime of s is less than 0, and from here to that we have a maximum turning point. Alright, so this one here, the point at which this one is occurring, the point at which we have a minimum turning point, and all of a sudden it changes to a maximum turning point. The point over there here, where the changes occur, where the graph changes direction, is called the point of inflection. Alright, and the second one, f prime prime of s less than 0. So here we consider this one and that. F prime prime of s less than 0, we have, if f prime prime of s less than 0, we always have a maximum turning point. Alright, so this is our maximum turning point. If a is between s, so that's the interval. And f prime prime of s greater than 0. So f prime prime of s greater than 0 is referring to this one. Okay, so we have a minimum turning point. So the point on the curve where we have a maximum turning point, and then when it got to that point, it changes to minimum turning point. Okay, that point here is also called a point of inflection. So point of inflection is generally when the graph changes direction. Alright, so have that in mind, and I think you are good to survive. You are good to survive with it. So this is basically what we refer to as point of inflection. Alright, so we look at the second derivative test, and I said earlier on, the second derivative test is purposely for finding local extrema, that is local minimum, local maximum. Okay, so we are going to see how to use how to find a local extrema using the second derivative. Look at the second derivative. Second derivative test. So again, we have to write something. We suppose f is differentiable on an open interval containing C and f prime of C is equal to 0. So let's look at some conditions. We first of all suppose f is differentiable on an open interval containing C and f prime of C. Right? This thing is very important. It must hold before we can write what we're about to write. So let's look at something. 1. F prime prime of C, if f prime prime of C is less than 0, then f has a local maximum So if f prime prime of C is less than 0, then f has a local maximum at C. So what this one means that you find your critical values, you find your second derivative of the function given. Then you find the functional value of the second derivative at the critical value. And if the value that you get is less than 0, it means at that particular critical value you use over here, the graph will have a local maximum. You see a maximum turning point. So the graph will have a local maximum at this point. Okay, let's look at the second one. Okay, so you let me maintain it. I think I will use it over very soon. So let's look at the second one. It says if f prime prime of C is greater than 0, then f has a local minimum at C. Okay, so if f prime prime of C is greater than 0, then f has a local minimum at C. So here, f prime prime of C less than 0, local maximum. It means here f from here to here, from this point to that point, f prime prime of C is less than 0. Okay, and here it's like it has a minimum turning point. It means f prime prime of C should be greater than 0. The same thing here, f prime prime of C should be greater than 0. Whenever we have a minimum turning point or minimum value, f prime prime of C is always greater than 0. And whenever we have a maximum turning point, f prime prime of C is less than 0. So in using the second derivative test to find local extrema, you just evaluate it. You just see here you are not going to find the functional values, okay, and compare. You just evaluate the second derivative at that critical value. You just observe the sign, irrespective of the magnitude of the value. You just have to check the sign. So if the sign is greater than 0, or if it is positive, then you say that the function will have a minimum value at that critical value. And if the sign is negative, then you say that the graph will have a maximum value at that critical value. Alright, so this is basically the second derivative test, and for better understanding and for clarification, we'll have to take an example. You have an example. It says if f of x is equal to 12 plus 2x squared minus x exponent 4. Use the second derivative test to find the local maxima and minima of f. We are also asked to discuss concavity and the point of inflection. So this question is actually a loaded question. We are going to do a lot of work over here. If f of x equals to 12 plus 2x squared minus x exponent 4, use the second derivative test to find the local maxima and the minima of f. We should also discuss concavity and the point of inflection. So let's begin with the solution over here. So the solution, we have this. So in finding using the second derivative test, we need critical values. So first of all, how to find the critical values? We are given that f of s equal to 12 plus 2x squared minus x exponent 4. So f prime of x is equal to 4x minus 4x cubed. So for critical values, f prime of x should be equal to 0, which implies that 4x minus 4x cubed should be equal to 0. Alright, so here we have to find for x over here, and so that we can factorize 4x out, and we have 1 minus x squared equal to 0. So we have x to be equal to 0, or 1 minus x squared equal to 0. So here we make x the subject, and we get x equal to 0 or x equal to plus or minus 1. Alright, here when we make x the subject, we get plus or minus 1. So we write so our critical values are the critical values are 0, 1, and minus 1. Alright, so here again, before you write all the critical values, we observe f prime of x, and we have 4x minus 4x cubed. Sorry, 4x cubed. Very good. And you see that the derivative is a polynomial, so there is no instance that the polynomial will be undefined. So we say that it is defined throughout its domain. So we strictly have our critical values to be what we found over there. Okay, so let's move on and find the local maxima and the minima, or the local extrema. So here, for the second derivative test, we have to find the second derivative of the function. So we have f prime prime of x is equal to the derivative of the f prime, which will give us 4 minus 12x squared. Alright. So for the second derivative test, we find f prime prime of c for all the critical values. Alright. And check which one is positive and which one is negative. At this point, we are not going to compare the values. We are going to check the sign. Okay, so we evaluate f prime prime of c for all the critical values. So f prime prime of 0 is equal to 4 minus 12 times 0 squared, which will give us 4. And this is greater than 0. Alright? And we find f prime prime of minus 1 to be equal to 4 minus 12 minus 1 squared. And this one will give us 4 plus 12, which is 26. Sorry, 4 minus 12, okay, is minus. And this one will give us minus 8. And this one is less than 0. We find f prime prime of 1, and we have 4 minus 12 times 1. And this one also gives us minus 8, and this is less than 0. So we observe something here. We observe something here, and we see that for the critical value 0, f prime prime of 0 is what? 4, which is positive. So whenever we get f prime prime to be positive, we say we have what? Local minima. Okay? And whenever we have f prime prime of c to be less than 0, we have local maxima. So the graph will have a local minima at s equal to 0, and its value is 4. And we'll have a local maxima at s equal to minus 1 and 1, and the value is minus 8. So let's write something here. So f has a local maxima at s is equal to 1 and s equal to minus 1, and the value is minus 8. F has a local minima at s equal to 0, and the value is 4. Alright? So that's what we have over there. So now we move to finding, or we said we should discuss concavity and to find the point of inflection. You see, the point of inflection plays a vital role in discussing concavity or in determining concavity. We can't talk of concavity without mentioning point of inflection. Okay, it's very, very important. So you have to find the point of inflection, or where the inflection occurs, okay, before we be able to discuss concavity. So let's find that. Inflection. So the point of inflection or inflection. So to solve for inflection, we say that f prime prime of x should be equal to 0. To find where the inflection occurs, we have to solve this equation, f prime prime of x to be equal to 0. Okay, and what was our f prime prime of x? We had 4 minus 12x squared. Okay, f prime prime of s is equal to 12x squared equal to 0. So you have to solve for this. We have 4 is equal to 12x squared, and we have 1 over 3 equal to x squared, and this implies x equal to plus or minus 1 over 3. Alright, x equal to plus or minus square root of 1 over 3. Okay, so what we have to do is okay, let me put it this way and put it this way. I want to always make it very simple for better understanding. So let's say we have the interval and we have f prime prime of x equal to 4 minus 12x squared. So for the interval, we have from minus infinity to minus root 1 over 3. We also have minus root 1 over 3, minus root 1 over 3, to root 1 over 3. We also have 1 over 3 to positive infinity. Alright. So this is what we have for the point of inflection, and most at times we include the critical values in determining the concavity. Okay, so I think this one too will give us the same results. Okay, so let's just use this one and we'll be fine. Alright, so I think this one will take a lot of time. Let me just use what's in the book. So we let minus 1 to belong to minus infinity minus root 1 over 3. So when we take this one, so I let minus 1 belong to minus infinity minus 1 over 3. So f prime prime of minus 1 is equal to minus 8, and this is less than 0. Okay, so whenever we have f prime prime or c to be less than 0, what do we say that we have? We have concave downward. We have concave downward. So concave downward is actually referring to maximum turning point. Okay. So I let 0 belong to minus 1 over 3, square root of 1 over 3, root 1 over 3, and we have f prime prime of 0 to be equal to 4 greater than 0. So since we have a greater than over here, we are going to have concave upward. And concave upward is talking to minimum turning point, okay? This is that the concavity is going up. So this one we have a minimum turning point. So I, when we consider a number in the interval with 1 over 3 positive infinity, we have f prime prime of 1 to equal to minus 8, which is less than 0. So on this interval we have concave downward, which is referring to a maximum turning point. So one may ask, where from this 0, 1, so where from this minus 1, 0, and 1? These are values that we picked from the interval, okay? So this minus 1 will lie within this interval. You can pick any value which will lie within this interval. And this 0 is coming from this interval. You can pick any value there, and the 1, you can pick any value there. And in both cases, we are going to have the same results over there. So let's look at something. So we say that finally, f is concave downward on the interval minus infinity to minus root 1 over 3 and root 1 over 3 to positive infinity. So second, is that f is concave upward on the interval minus root 1 over 3 to root 1 over 3. So that's what we have for the concavity. Okay, as I said, you can also include the critical values. Then you find the interval between minus infinity to that minus root 1 over 3. Then from minus root 1 over 3 to 0, minus infinity to minus 1, then minus 1 to minus 1 over 3, minus 1 over 3 to 0, 0 to 1 over 3, then 1 over 3 to 1. It's going to be going to be plenty. So I think this one is somehow enough. So let's continue. We are asked to find the point of inflection. So what we found earlier on, this one, plus or minus root 1 over 3 are the values at the point where the point of inflection occurs. So let's actually find the point of inflection. So we can do that by, I think you need some seconds to finish writing this one. So you have 30 seconds to finish up. Alright, so I assume that you are done writing it. So where, let me clean this place. So we are finding the point of inflection, and we say that F has inflection points as F equal to minus root 1 over 3 and F equal to root 1 over 3. Alright, so let's find the point. So whenever we have an x value, we can always find a point. We substitute it into the function given to find the corresponding value of y. So we have f of minus root 1 over 3, and this one is equal to, so here you have to put minus 1 over 3 into the function given. Alright, so you substitute it there, and we have 12 plus 2 square root of minus 1 over 3 squared minus 4, minus square root of 1 over 3 exponent 4. And when we do everything, we are going to get 113 over 9. Then you do it for root 1 over 3. And similarly, when you substitute inside, you are going to get the same value, 113 over 9. Alright, so the inflection points are now the x and y values. So the inflection points are we have minus root 1 over 3, comma 113 over 9, and root 1 over 3, comma 113 over 9. So this is our point of inflection, and to the glory of God, we are done with concavity and the second derivative test. So you find more examples, you solve on it, and you'll be fine. So in our next video, we are going to talk about optimization problems, okay, which involves differentiation and a whole lot. So see you in the next video on optimization problem. Thanks for watching, and try as much as possible to like the page and also subscribe to my YouTube channel, Think Math, Think Father Noah. Thank you.